Welcome to a new test and teardown video. This time it's a switch mode power supply from EA. It's called EAPS 2042-10B. Yeah, like I said, 0 to 42 volts and 0 to 10 amps. But only 160 watts in total output. It's one of those super modern one with USB interface, encoders. See, they just rotate and rotate. The software interface, everything is completely software interface. But there is a problem with the design here. As you can see here behind the screen, dust gets in to the screen. So it's like, this looks like it was, well, I don't know, used on the beach or something. It's full of sand or dust. So I will have to clean that. We can see some screws here for our different power components. And that is of course the description label here on the back. It is not even mounted straight. So they just did this really fast and didn't care for detail. I know there's a little bit of a problem with this one. So I can't wait to show you exactly what is the problem. But we need to open it first and see if I can fix it. What the heck happened here? And this smells a little bit special. This kind of dirt. It's just full of dirt all over the place. Wow, that is one big transformer. And then we got, one is the transformer and one is the inductor, I guess. Yeah, that's exactly what it is. So this is the output smoothing inductor, and that one will be the transformer. And what else have we got? We got the diodes. See, those are just regular diodes. And they're just cooled using the circuit board to the chassis and to this piece of metal. That will be the primary side, so it looks a little bit like a half bridge. Yes, this is just a half bridge. And that is just the main topology of this power supply. And then input filter, that is all that stuff behind this little cooler here. It's really not impressive. Oy. Yeah, I need to go clean this up a little bit. After a little bit of compressed air, it is now nice and clean, and we can see what is going on here. So on the primary side we got a half bridge, right? And then that will be the sense resistor for the current mode. We got some snubber circuits, and that's of course the transformer. We got some diodes. See there, they have to poke around with capacitors here to create the correct snubber filters. So all those capacitors here and the parts here, that is the secondary rectifier and filter. And then that will be the current sense resistors and output capacitors. Once again, so this, and we have a little inductor here. So that is of course also output filter. I think also both this and these. So we got 3 capacitors here that they form the output filter system. And look at that, the common mode output choke. So ground goes through that filter, and this is the positive output. So that will be the thick one. But see the thin yellow wire that also goes through this common mode choke. That's of course the sense signal. And out here they're using almost same thickness wires for the output and for the sense. And here's another funny thing. Look at all the capacitors. I mean, it looks a little bit like not that pro level, to be honest. So here is the microcontroller that's doing all the software. I said earlier in the video, this is a complete software interfaced and controlled unit. So we've got a little microcontroller there. It looks a little bit like an STM32. Some line driving port expansion. And it's driving then the LCD. Everything to the LCD, including the encoders, USB, and all that goes in this flat cable. Isn't that amazing? So there's no other wires, as you can see, going to that display. So maybe there's another little microcontroller on that board handling some other stuff, because we also got some transformers here for communication, so that could be USB filter. Well, I think we have a USB chip down here or something like that. So I need to go in here anyway to clean out the dust inside the display. Down here we got a few op amps for the software integration, the software handling of everything here. This is a little current sense amplifier that is connected to the very, very low value. It says actually 0.2 on these. So that is I think that is what it is, right? So that is milliohms, right? So that will be a total of 1 milliohm. So of course you need a lot of amplification so you can read this current sense signal. So now we're inside the back of the display. Quite easy to get in here. I really want to show you this, and this is something many designers do wrong. Can you see what happened to this screw? It's full of plastic. It's actually the whole hole from the plastic here. Well, not exactly that one, because there was one where it didn't happen so much. But all the other three, look at that, the entire hole came out with the screw. And this is simply because they made the holes in the plastic round. So that means something that is round cannot expand when you put in a screw. And this is a very, very fundamental thing to understand when you create plastic molds for self-tapping screws. If you make it the whole triangle or rectangular or square, any other shape than round actually, then the hole can expand, the plastic can expand a little bit, and this way take up the diameter of the screw and still be intact. And this way create a good plastic thread as well for you. So it was designed wrong by people who don't know this fundamental little problem. So now we're inside the back of the display. And here's a problem. This is the glass. And can you see there's a hole? And they glued the glass not in correctly. Why isn't it aligned correctly? And just tiny little drops of glue. I mean, if you crack this out and put it correctly in and glue it all the way around, I mean, you can't get dust in here. See, it's full of dust, and that is on the back side. And also the display here got some dust here. So there was definitely another little processor here. And as you can see, this is the LPC. and that one is doing the USB. And then there's another high-speed communication between this one and the main power supply regulation CPU up there. And everything is now in this little flat cable. So that is our encoders, also full of dust. This can't be good. They are mechanical encoders, so we got two contact tracks and two sliders that goes around here and creating the 2-bit gray code by contacts. And what have we got up there? Another little IC, whatever that is doing. Port expansion, something latches and stuff for the LCD interface. And there's a little background light there. So that is more or less what there is to say about this software debug. This one says artikelnummer platine bestückt, so this means that there's a number for this board with all the parts mounted. Then it has a new number, and that number you should put there, but they didn't do that. Funny. Or is this a sticker maybe you should put there? I don't know. Yeah, I'll have to clean this a lot more and see if I can get it real nice. Oh, look at that. The back side of the contacts. Can you see that? This is out of focus. Here you go. SMD capacitors. Look here between the pins. So they're trying to remove some glitches from the contacts using capacitors instead of fixing this the correct way in software. This could also reveal that the software for reading the encoders, that's just really not made correctly. And this leads me a little bit to the problem there is with exactly the whole line of these units, this whole line of power supplies. They are just absolutely unreliable, and they can, by random interval, give you full output voltage. It's because the software reads these and it communicates to the other one, and somehow there is no limits in the software for checking or verifying or step responding or anything like that, or verifying that you actually did want this change. No way. It just hammers out full voltage without any warning, and then you blow up whatever it is you have connected. You can imagine this thing can do 42 volts. So if you're playing with something for 5 or 10 or 12 volts, and then suddenly you go away for a cup of coffee and come back and everything is in smoke. And that is definitely what this power supply is famous for doing, because the whole design is just absolutely wrong. So I wanted to try and repair this. So I broke off the little glue points to move it in correctly into the slot. But of course now it's bent, because what they did is they just glued it wrong and then pressed in the glass display. And now this glass is bent. I mean, this is of course not in the bad design, but this is in bad manufacturing. And again, look at the holes. Again, all of them, they are round, and then this plastic here cracks. And it's just really bad design. Also, a very funny manufacturing decision here is to make these holes in the other PCB like that, and then you need to mount the circuit board with both small screws that goes into these little holes, and then larger screws that goes up here to hold that circuit board. So it's double as many screws, and just a little bit annoying to assemble. Why would you do it this way? It's so complicated. So here we go. I think I'm ready to assemble this again. I use transparent contact glue all the way around here. I think I tried to make it as dust tight as possible. And now my display is nice and clean. And I will try and see if I have any luck. Let's play a little bit with this unit after it's been completely cleaned and assembled. That's the AC output. Oi, oi, oi. What do you think about that? We got DC 0 volts. And let's try and see if we can figure out how to operate this thing. So you have to push. Hello. So you don't know where you are. You just have to turn on the voltage, and then you can what is this? Ooh, super dodgy setup. So that is 6 volts. Let's see. Okay, so it responds. So this is I am in 1 volt step. And what if I click it? I have no idea how to. That is just the worst of the worst. And how about that? You have no clue about your current setting. So if I turn this off, then what can I do here? No. So preset. See, if you push in preset, then you can see your voltage and your current settings. So this is the way you set your current limit. So this is just the most dodgy. And here I got quite a nice resolution. But what about, okay, voltage is just 1. Oh, voltage, So here you can check, you can set this up. So if you're working with some 5 volt stuff, you can set this to 6 volts. So it will over voltage protect at some really low voltage. Okay, that is very useful. Ooh, good, and then what else? Lock 4 second. No, we don't want that. And then we can output on. Okay, but you can only step the output in 1 volt unless this switch here is not working or I'm doing something completely wrong. Look at that. Look what happened. I held it in. And now I have 50 millivolts of step. So if I click it, no, so you have to hold it and then, okay, so it is a hold and then it is the most dodgy interface. And you have no indication of what you're doing, but at least now we know a little bit of how that works. And the voltmeter seems to be quite all right. It's not super bad. I think I'll try and load it a little bit and let's see on the output. This is 100 millivolts per division, by the way. Oi, oi, oi. So we're trying to loading it a little bit. They say 160 watts, that is the maximum. And you kind of need to be under that, just barely under that, then it will work. Otherwise it's gonna crank down the output. So it's doing the math on the output power. So that means you can of course not pull 4 amps at 40 volts. But you need to be just below that. So here's 3.9 amps. And I'm measuring still the 40 volts output. So that is 156 watts of output. The power consumption on the input, AC mains input, is 177.8 watts. So that means a total efficiency of 87.7%. So that is quite high. And this also explains why you see these tiny little heat sinks, because it's really not getting warm. I mean, I have 155 or 56 out in total. It's not that many watts that I'm losing inside this unit, is it? It's always interesting to check it out. It's still running and at full load. And now we can see what gets warm. So that will be all the resistors down in the primary side. And what have we got here? We got some resistors at 100. What else have we got? Inductor, transformer, not that bad. We got a little resistor down there, 70 something. That is a little resistor down there. Yeah, you can even see a component on the CPU card there getting warm. That's interesting. Output, filter. No, not a lot. Oh, that will be output discharge resistors down there, I guess, right? And of course they also run quite warm because I have it at 40 volts output. That will be the rectifier stuff. And that all looks perfectly fine. I think what I want to do is I want to stop my load and then see the idle and compare the idle with all this and how it looks when it's not loaded. So now it has been running idle. That means no load for quite a while, and we can have a little look on temperatures. So I'm still at 40 volts output, and there you have it, your discharge resistors. And what else is warm? Down here on the in here is all the primary side resistors, still running a little bit warm here. Definitely also that one. And yeah, actually all those power resistors, they're still getting nice and warm. And there is actually a little thing I want to show you. Let's have a little look again. I mean, you got all the rectifiers and all the filters and stuff in here, right? Here's the rectifier and all the filters down there, right? But what is missing? Do you see it? We don't have a capacitor. So that means mains input is rectified using a bridge. And this is probably the only tiny little capacitor to the primary half bridge transformer and all that. So that means this thing is not running on DC voltage. It's running off a rectified AC with no capacitor. So that means when you look at the output, you see this. This looks like a pulse skip mode, and that is actually also what it is. So if we look at the output here, you can see I am now in 2 milliseconds per division. So this is of course mains frequency related, right? And that means it is switching and regulating and all that kind of stuff on tiny little pulses that is in phase with incoming AC. And let me try and show you what I want to show you. So here is source for trigger. Let me go into AC line. So now I'm triggering on AC line, and you can probably kind of envision we got some sine waves here. And what I also can do on this scope, I can add a little bit of persistence. So there you have it, your AC line, and this is the way that this system here is regulating, and that is just to make it super cheap, because big capacitors on high voltage and all that kind of stuff, they're of course expensive, and you don't want to have any expensive components inside your power supply. So yeah, there you have it. So let's try and go into DC mode. Here's 0 volts. I got 1 volt per output, and this is now 5 volts. So now I'm using this power supply to drive something at 5 volts, and my current is 4 amps. And this is how it looks like. So as you can see, it's quite a lot of noisy ripple. And then I turn off my load, and then it looks a little bit like the funny pulse skipping mode. And what you see here is, of course, your mains frequency. Again, let's try and show you AC line triggering. So that is definitely a nasty, noisy power supply. You should also always talk about bandwidth when you talk about noise and claiming something is noisy. Because, of course, this is noisy, yeah. But the frequency range of the noise, I am now in full bandwidth, so that means it's 500 megahertz. And then I go down to 200 megahertz, and you see it actually a little bit less. And then I go to 20 megahertz bandwidth. And now it's really not that bad anymore. So if you have correct filters and you did design your electronics correctly for the bandwidth that you're using, obviously you shouldn't be affected by this, because you will have filters on the inputs of your stuff if it's correctly designed. I've been playing a little bit around here with this load. I think my setup here turned out to be a little bit crazy. First, I played around with the Siglent load here and the programming and the setups. And of course, this thing is connected via Ethernet, and I can do all sorts of stuff by remote. But it just wasn't funny today. I wanted it to run on this unit alone, okay, but there is no loop. There's no loop in this programming. How lame is that? Anyway, I wanted to try and free out this power supply and see if I can somehow make it unstable, because that is the error report I heard from many of the users of this particular unit, and it just goes crazy. And the last time they played with it, they were running neopixels, and quite a lot of neopixels on 5 volts. So to simulate a very random power usage, I have my 4 input, or my 4 separate loads with individual enable, disable, and it's actually an analog input to that optocoupler. So what I'm doing is, as you can see here on the meters, can you see they're all running completely 3 running individual currents, and all this is of course added together to create a completely crazy random load. So to run the inputs here, I got one signal generator here and another signal generator here, and I'm of course controlling the high-low levels for the trigger, so I can find the sweet spot for analog behavior and digital behavior and different timings, and nothing is of course having the same numbers of the timings, right? So this is now the output. I'm running in roll mode, 100 seconds per division, and then I'm just monitoring this, and hopefully I will see something. Otherwise I will call it a bogus, I don't know. Maybe it just don't fail when I test stuff. Of course, only test if you have neopixels or anything else connected that will actually blow up. There's one small little detail I also want to document about this power supply. The whole user interface and the whole idea about it is just so bad in many, many cases. And let's see. Output is set for 5 volts, and the circuit is on here, right? So if I turn off my power supply, and tomorrow or some other day I want to continue my experiment, so then I turn on my power supply, and then you get 0 volts, 0 nothing, and I mean I could live with that, and then you just hit on and then you get nothing. So don't remember anything like that, right? So let's let's try see. Now it's off. Now it's on. Okay, off again. Then I touch the voltmeter a little bit up. Okay, now I turn it on. See? It is, that was actually by sheer luck that I turned it that much for a 5 volt. I just tried this before and I just hit 4. But it depends on how many clicks. I just did 5 click, and that is exactly like that. How cool is that? But you see, if it's on or off. So now it's off, it handles a volt setting in off mode, but don't display anything. So now it's on and you have 2 volts. I mean, really? It is just really, really bad. So I let this test run the whole day. I don't know if you can see this, it's getting dark. So, and I don't see anything at all. The scope is still in roll mode, and we have 1000 seconds per division. So that is 16 minutes per division. That also means this entire screen is 2.7 hours. That is some crazy sweep times here, right? And it's just not failing whatsoever. So I don't know. I'm not able to recreate that weirdo thing, but I was told that it's completely unstable and it will continue to go to all sorts of crazy voltages now and then. And I can't recreate it. That is really, really sad, because I really think that I got the most fantastic setup to prove that and to document it, and then to go and yell and scream about how bad it is. But I just have to, to trust what people say. I can't make the curve myself. So I think for now, I'll just end this video and hope you had a little fun. Bye bye.